I just crossed out L3. I'm switching to L4 and L5. So these are my last Lagrange points. So just really quickly, let's go over the whole deal. These are hard and easy to calculate, 4 and 5. Okay, so I have this binary star system, or a mass and a planet, whatever, M1 and M2, and they orbit each other. M1 is larger, so they orbit a common center mass. And so I got this program set up so that these orbit in a stable circular orbits. They have different sizes because they have different masses. And then I can calculate the R1 is the orbital distance for mass 1, R2 is for mass 2. I give it a parameters mass 1, mass 2, and the distance between them, capital R. So I can calculate R1, R2, their velocities, the angular velocity. Okay. Now, a Lagrange point is a location in space. There are there's 5 of them, where you place a low mass object and it will orbit at the same angular velocity. So here's one right here. Here's the L3 Lagrange point. At this point, there are 2 forces on this. There's the gravitational force due to M1 and the gravitational force due to M2. And the combination of those 2 will give this an acceleration that makes it move in a circle with the same angular velocity. So you have L3, here's L1, it's right here. And then there's another one right there, L2. So 1, 2, 3. And I'm going to find points 4 and 5. So let's draw a new picture. But I wanted to start with this because I didn't want to rewrite these things. Okay, so here is, and I'm doing an exaggerated view, right? So I have M1 is, if it was the Earth and the Sun, I mean, the Sun is M1 and essentially at the center mass because the Earth is so puny. So this is M1, and this is R1. And then here is R2, and that's M2. Okay, so I think L4 is up here. I can't remember it. Let's see, actually put it right up here. Right about right there, L4. So L4 is at the tip of an equilateral triangle. So this is R, and this is R, and this is R, and this is R. So these are all 60 degrees. And so if that's true, am I still recording? Yeah, what happened? If that's true, then the gravitational force on a mass at L4 would be pointing straight towards this center of rotation. And so what I'm going to do is kind of plausibly set this up for you and show that it has to be an equilateral triangle. And then I'm going to just model it from there. I'm going to calculate the actual location for a situation, and then we'll talk about some stuff. I don't want to fully derive that has to be an equilateral triangle. So let me start by flipping this like this. And I'm going to redraw this, but I'm going to put the L4 at the origin, and then put actually M1 and M2 over there. So let's say here's my origin. And this is L4. And now I have, let's say, M2 right here. I'm going to draw this as, this is M1, I'm sorry. And then this is, I'm going to tilt it a little bit like this. M1, and this is going to be the vector location from the origin of mass 1, R1, and this is the vector location of that R2. And what I want to do is find the center of mass. So I can use this. R center of mass is going to be equal to M1. I got these backwards. That's 2, that's 2, that's 1. I don't know what I was thinking. I flipped the whole thing up and I kind of got myself confused. M1 R1 vector plus M2 R2 vector over M1 plus M2. This is just the definition of the sum of over I, Mi, Ri vector over M total. It's the same thing, but I only have 2 masses, right? That's the summation. So that's the location of this, our center of mass. Now what I want to show is that the net force on this object here, and in fact I'm going to use the gravitational field. The net gravitational field due to these two is pointing also in that same direction. Because if this is going to move in a circular orbit about that point, then there needs to be a net force there. Because remember, F net equals ma. And if it's moving in a circle, the magnitude of the acceleration is going to be equal to omega squared times r, where r is the radius of the orbit, which I don't actually know at this point, but we're going to calculate that explicitly. So this is my definition of center mass. What I need to do is find the gravitational field. So I don't want to deal with the gravitational force because I don't want to put a mass there. I'm just going to put the gravitational field. So G in general, the gravitational field is G m1 over r hat. I think that's fine. Negative, technically. So this is the gravitational constant. This is the mass of that object. This is the distance from that object squared. From that to that squared, and this is a unit vector because I need the unit vector in that direction. Okay, so the total gravitational field at this point is going to be equal to the one due to m1 and the one due to m2. So I'll put G equals G m1 over this. Okay, so that distance is going to be equal to, I'm setting that, I already know the answer. This is an equilateral triangle, so all these sides are of length r. So I'm going to say over r squared, that's the distance. But now I need to multiply it by a unit vector in the direction of r1 hat, so that it's in the correct direction, and that's actually negative, r1 hat. So that's the gravitational field due to mass 1. Now for mass 2, it's going to look the same, minus g m2 r2 hat over r squared. So I can factor out a g and an r squared, and I get negative g over r squared m1 r1 hat plus m2 r2 hat. So this is a unit vector. A unit vector, we define r1 hat as the vector r1 divided by the magnitude of r1. So it has a magnitude of 1. Now, but this means that I can actually write r1 hat. I can write the vector r1 as the magnitude of r1, which is this distance right here, which I've already said is r, times r1 hat. So if I use that up here, then I can write this. R center of mass equals m1. r1 is going to be this, r1 hat plus m2 r2 hat. I can do the same thing for r2, divided by m1 plus m2. So if I can factor some stuff out, I get r over m1 plus m2 times m1 r1 hat plus m2 r2 hat. And there, that tells me the direction of this, the center mass. And that's the same direction, that's the same vector right here. So they just differ by a constant out front. So that tells me that if this is an equilateral triangle, if all these distances are the same, this distance has to be the same as that distance, or this won't work. I can't factor out that r. Okay, but if I do, then the location of the center mass is the same direction as the net gravitational field. So this gravitational field points that way. Now, what I need to also show is that the magnitude of this gravitational field, which I didn't calculate because I can't add up R1 and R2 together. I can't do this, right, unless I know what those vectors are. That would have to be equal to the magnitude of this, which is, I think I could figure this out with just triangles. Actually, I'm thinking you can use the law of sines and cosines or something like that. So this distance is proportional to, so that what I want to show is that this, I want to show negative g m1 over r squared, actually pull it out, m1 r1 hat plus m2 r2 hat is equal to the acceleration, which would be omega squared, let's call that r com, center mass, just the magnitude. I want to show that. Okay. So what I'm going to do is the following. I'm going to take my gravitational system that I already have. And so it looks like this. So there's M1, there's M2, and this is the distance r. That's the origin. That's R. I want to start right here, and I'm going to go up 60 degrees and add a vector that has a direction of 60 degrees and a magnitude R, and that's the location of L4. And so I can put it there. I can put an object there. Now, I want to model this and see that it stays there, so I also need to calculate the initial velocity and the momentum. So I'm going to use this. I know the angular velocity. I've already done that. So I can say V equals R cross omega. So I'm going to do a cross product. Over here, what I did when I put an object there, I said it's in the y direction. But now at an angle, it's a little bit more complicated. So if the angular velocity is in the z direction this way, and R is that way, the vector R is that way, R cross omega is that direction. So I can use that. So let's just go ahead, jump over to Python, and see if we can make this thing happen. I should also point out that if the mass of this object is very large, then the distance from here is the distance to there, because this is shifted to the center mass. But we want to be able to do this for non-simple situations. Okay, so let's switch over to Python. So this is the last program that I had. This is for the L3 orbit. Let me just run this real quick. I calculated this RT with another program, and I copied it in there. And you can see that they both orbit. RT is not the same as the vector here because this is not at the center mass, but it works. So ball 1 is my location. So let's. I need to calculate. I already have the value for R. So I want to calculate this vector. I'm going to call it VR. It's going to be equal. Let's put this angle theta in there too. So let's say theta equals 60 times pi divided by 180. So that's the angle between. I have everything on the x-axis. So that's the angle up from the x-axis I'm going to have. So it's going to be equal to R times cosine theta, vector cosine theta. Can you see that's big enough? That's too big. I like that. Sine theta, 0. So that's the vector from here, but I haven't added it to there yet. So now let's calculate this vector RT. So RT I use as a scalar, but now I'm going to use it as a vector. So RT is going to be the vector M1. I'm going from M1 to there. So it's going to be star1 dot POS. That's where I made it up here. Star 1 is the yellow one. Star1 dot POS plus VR. Because I don't want to start from the origin. I need that vector from star 1. Okay. So now down here, the position, I'll just change this to RT. And then down here for the initial momentum, you see I was already practicing up here. Actually, I can just copy this out and put it like this. So here I have ball 1 dot mass times the cross product of ball 1 dot position, because it's orbiting about the center of mass, which is at the origin. So I'm going to use the ball 1 dot POS is R for that ball. Okay, and then I multiply it by the cross product of the position R and the angular velocity vector, which I wrote as 0, W, which I calculated W, which is supposed to be omega, up there. Okay, let's see if it works. So it's behind it, and it looks stable. So I'm pretty happy. Let's just try real quick. What if I want to calculate the other position? Well, what if I just put in an angle of negative 60? Would that give it to me? Let's see down here. Theta is negative 60. That'd be the other one. I think that'll work. Yep. And it looks stable too. And it should be stable. Okay, now what I want to do is that's fine. I have my position, I have my ball. So I want to calculate just G. So G, I'm just going to type it out. G is negative G times m1, did I call that? Yeah, m1 times star. Okay, let's do this. Oh, I have it down here. Let's just copy that up here. Okay, so R11 is the vector from star 1 to the ball. R12 is from star 2 to the ball. So now I can say G equals negative G times M1 times norm R11 divided by mag R111 squared plus minus G times M2 times norm R12 divided by mag R12 squared. So that is the gravitational vector at that starting location. And let's print that out. Print G equals G. And don't worry about the units. So now what I want to do is to calculate the magnitude of the acceleration. So that would be, I need let's just say AC, the centripetal acceleration is going to be omega squared, which I already know, put that in parentheses, times the circular orbit radius, which is ball times mag ball 1.pos, because that's the R. And let's print that out. Let's print out the magnitude of G2. Print. I already know it's in the same direction, so I don't really care about the vectorness of it. Mag G. And then down here, print AC equals AC. Let's see what happens. Okay, there, it worked. Check that out. So the magnitude of the gravitational field is the magnitude of the acceleration. Let's see if I have a more binary-like star system. I think this should work. If I go up here, and right now I have a mass of 2 times 10 to the 30th, that's like the mass of the sun, and then 1 times 10 to the 25th, which is like a heavy Earth. What if I make that like 1 times 10 to the 28th? Let's see what happens. I don't see that other thing moving too much, but I think it is moving. Let's make it a little bit bigger. 29th. Okay, now you can see that they're not at the same distance. And you can see also, oh, my picture's in the way. Let's move that, I'm sorry. No one wants to see that. Okay, you can see, this is great. They're not the same orbital distance, right? But it is stable. Let's make it a little bit bigger even. Let's turn that to 5. There you go. Check that out. Okay, I kind of like that. I'm pretty happy. So now I have, I guess I should add L4 and L5 as functions in my other program. So I'm going to go ahead and do that right now while I'm at it. 18, I got time. That way I don't have to make another video, right? So here's my previous program that calculates L1, L2, and L3. So I want to go ahead and to do the same thing for def L4. And I need to give M1, M2, and R. That's all I need. These other ones had this iterative process of calculating stuff. I don't need that. I do need all this stuff though. Right there. And this will just return the, This one's gonna be different. Because the other ones I calculated the scalar value. But now I want to calculate the actual position. So if that's the case, I need to know the actual position of mass 1 and mass 2, not just their values. So I guess I could pass in I'll just use R1 as a vector and R2 as a vector. But I'll have to pass that in. Okay. So there's my function. Let me put this in there. That's weird. Okay. So I need M1, M2. That's fine. I guess I technically need R. No, I'm going to say VR1, VR2. So that's the vector location of mass 1 and the vector location of mass 2. And then this will return the vector location of L4. Okay. So I have all that stuff in here. Now what I need to do is the same thing I did over here, right? And the first thing is to have that angle theta. So theta equals 60 times pi divided by 180. Calculate VR is going to be equal to, so I didn't pass in R. So let's calculate R. So R is going to be equal to VR2 minus, it's going to be the magnitude of VR2 minus VR1. Right, because then I have that, if I have the vector from mass 1 to mass 2, that should be R, and I take the magnitude now of the scalar. So now I can say the same thing I said before, R times vector cosine theta sine theta. And this shouldn't matter where these things are, 0. Now I can calculate that RT. It's going to be VR1, that's vector for R1, plus VR. And that's what I want, VR. Now I can return RT as a vector. So let's try this out. Let's print up here before I do that so I know the answer. Star 1 here. Let's print RL4 equals, and that's just going to be ball1.pos. Yeah. So let's run that. Okay, so there's my location. Now, if I go back over here, and let's say print RL4 equals, now I need L4, the function L4. I need to give it M1, M2. Now I need the vector location of R1. So that's going to be vector negative R1, 0, 0. Yeah, so there I have it right there. And then the vector location of R2, it's going to be vector R2, 0, 0, because it's on the other side. And let's just see if that prints this out the same thing. I don't actually know that it will. I feel error coming. See, I felt that. VR2. VR1, VR2. Evaluating an object, VR2. VR2, VR, R times cosine theta, VR1 plus VR, VR2, VR2. I passed it in there. Vector R2, 0, 0. Oh, that's why. This should not be there. No? Missing a right parentheses in line 164. Okay. L4, vector. Oh. Anyone right here. I think. Yeah. No, it didn't do it. RL4 equals, oh, it's up here. Okay. 7 times 10 to the 10th, 1.2 times 10 to the 11th. Different. Oh, I did change that. I remember I changed this. So let's put this back to what I had before, which was 10 to the 25th. Oh, negative. What's that negative? Oh, that's right. I changed. I know why. Because that was for L5 actually, but it's the same thing. So that's good. Now I can just do the same thing for L5, and it should work fine. And let's change this to L5. And then down here, theta is negative. That's the only difference. And save it, and I'm done. So now I have one program that has the functions that calculates L1, L2, L3, L4, and L5. Now I can do some fun stuff with it. But I feel much better now calculating those things. And I'll give you the code below. If you're interested in this, I have a playlist with all of these in there, so you can go back and look at the other ones. But I'll give you this code in this thing. And I do have some other ideas. I want to make some plots of the effective potential. I want to look at stability. I'm not sure when I'll get to that, but it's on my list. So that's it.